All right, so today we're going to start chapter 3. Tomorrow's your test. So today we're just going to take the notes. You do have a homework assignment, but it's not really going to be talked about until Friday, because again, tomorrow is your test. So one quick reminder or concept idea from physics is we've done DVA before, okay? And the D stands for displacement, or a lot of times you think of height, but that doesn't start with D, or distance, okay? And V is your velocity, and A is your acceleration. And the way you can go about going from the D to the V, or the V to the A, is by taking derivatives, okay? Now, the physics part that I want you to realize, and I have some Java apps that we'll be looking at next week on this, is this fact. When speed is increasing, this happens when both V and A are the same sign. A lot of people think through it that anytime you're deaccelerating, if you're having a negative acceleration, then you must be slowing down. That's not true. As long as they're both the same sign, then you're good. The best way to think about those things is maybe like this example here is putting foot on gas and accelerating off of a stop sign, or from a stop sign, okay? Now, the negative part, too often we think of the word deaccelerate means slowing down, and it doesn't actually. Think about, what about this? Falling down, falling off the cliff. Gravity is the only acceleration, and that is negative 32 feet per second. And since you're falling, your velocity is negative. So since you're falling with a negative velocity because you're going down and gravity, it is speeding you up towards the ground. All the negative means is it's speeding you up in that direction. So if both are positive, you're speeding up in a positive quote unquote direction, and both are negative, you are speeding up in the backwards direction, okay? If it's opposite signs, that's when you're slowing down, because that's when velocity might be trying to go this way, but acceleration is trying to pull you that way. They're canceling each other out, so that is a slowdown, okay? And that's where maybe one is oriented as a positive and one's a negative, then it's both slowing. But when it is both down, they're helping each other out, so it's speeding you up, okay? We'll be using that when we start doing some applications of things, but I thought I'd just give it to you for now as well. So if I ever talk about a particle and I say, here's your displacement function, it wants to talk about acceleration, how many derivatives do I need to go from displacement to acceleration? 2, okay? All right, with that said, just a little physics talk before we really dive into this chapter. This chapter, chapter 3, you're going to be learning how to become a human graphing calculator, okay? So you're going to be smarter than a TI-83, and you'll be able to graph, and you'll be able to know when things go up, when things go down, when you have maxes and mins, and how it bends. That's something that's going to be new today for you guys. So, first derivative stuff that we'll be working with, you've already done these things. First derivative will tell you when to sketch up. That's when you have a positive slope. It will also tell you when to sketch down, which is a negative slope. And the most important slope is not when you're going up, not when you're going down, but we've been talking about it before with the horizontal tangents. Most importantly, when you possibly can turn around, and that slope equals 0. That's the whole idea of the horizontal tangents. Okay? So we've been already doing this before where I have it like that, and you guys have been going negative, 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 positive, 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 negative, 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 positive, 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 but most importantly, slope of 0, slope of 0, slope of 0, okay? Because those give me where I could have a max or a min or another min, okay? The big new thing from this chapter is going to be how things bend. So I could have the same idea, but maybe look how this bends. If I bend it differently, and maybe this bends differently, and maybe here I bend it there. If you notice, the slopes are still the same. Over here it is negative. Here it's positive. I'll do it in green so you see it. Here it's negative. There it's positive. There it's negative. There it's positive. There it's positive. And yes, at the same points here, my slopes are zeros. But you see how it bends just a little bit differently. Especially over here, I think you can see it because I drew it pretty well, where this zone here, right here looks the same in a sense. This kind of bending down, and this seemed to bend down. But then do you notice how at the end of that, all of a sudden, I still kept a positive slope, but it seemed to be bending up there? That's the whole idea of the second derivative. And we'll be looking at this next week. But the second derivative talks about concavity. And concavity showcases how a graph bends or curves. Okay? So not if it's going up or going down, but rather how it bends. So I drew some examples here. There are 3 types of bends that you could have. There is concave up, which is where you're bending up. That's the blue guy. You have a straight line or no curvature, so it's not bending up, it's not bending down, it's straight. That's when it's no curvature. And then you can have concave down, and that's when it's bending back towards the ground. Now notice, I'm saying the second derivative is positive for the blue guy, second derivative is 0 for the red guy, and the second derivative is negative for the green guy. Different second derivatives, but all of these have the first derivative as positive because they're all going up. Okay? And I could extend this if I wanted to and show you where the first derivative could be negative and still be concave up. I can show you over here where the first derivative could be negative but still concave down. So you can have the concave up or down regardless of the first derivative sign. Okay? So this whole human calculator thing is I'm going to teach you how to figure out when the graph is going up or down or flat. That's the first derivative. And then I'm going to help you find how is it going up or down or flat. How is it bending while you do that? Okay? So again, it could be this whole idea of, let's say you know 3 points. And you know that it goes up here, it's flat there, and it's down to there. One way to draw that is I can just say, oh, up, flat, oops, and down. Okay? But I could also draw up, flat, down. Those still satisfy the first derivative part, but it bends differently. So my goal for you guys as a human calculator is not only knowing how to plot points and then how to figure out slope, but then also to figure out how it bends. Okay? So we will talk about that. By the way, before I dive into this, I just want to note here, anytime you're at an endpoint, okay? So right now I've already said that both of these are going up in this zone. They're both flat there. They're both negative there. At endpoints, this is very important. At endpoints, there is no derivative. You can't tell me slope because you are on a cliff. Think about this. What's the definition of a derivative? It's the slope of a tangent line at a given point. So who is to argue that at that point, that to me looks tangent to either the red or the green because it only touches it once. But I could bend it, and I could kind of put it right in the middle of the red and the green. And again, it looks like it's a tangent line because it only touches once. Okay? I can make it really steep and have this. Okay? This should remind you of the cusp idea, where at the cusp, it's too hard to figure out the tangent because it's like a seesaw. The same at the endpoint. Okay? So at endpoints, there's no derivative. It is undefined because it's just hanging off of an edge. Okay? So let's actually dive into a problem, and let's look at this section. Oh, I didn't want to take a picture. This section here. Extrema, which is saying maxes and mins. So the word extrema means find maxes or mins on an interval. So it says graph this guy on -1 to 3. Label all local or global maxes or mins. I'll talk about what local and global means in a second. So write this down, and then we'll take a look at it in 1 second. All right, so let's take a look at this. So we have f prime of x is 2x minus 4. A lot of times when maxes and mins happen, when is that for the derivative? And the slope equals 0. So 2x equals 4. So x equals 2. Now, quick sketch. This is a parabola. You already know what parabolas look like. They are either up or down, and it's a positive one, so it's like this. Now, we just found out that this is at x equals 2. That's nice. Here's the part that's different for today, unlike when we've done the parabolas before. I put it on an interval from -1 to 3. So let's say right here is 3, and let's say right here is -1. What that means then is I need to cut off the rest of the parabola. And right when you cut it off, what have you created? You've created another possible max and another possible max because you cut things off. So there's definitely some high points and the low point. We found the low point. And I know the high points are at -1 and 3, but I want to see where they are. So a great way to organize all this data is in a chart. And this chart, and we're going to be doing this chart the rest of the day, is this looking. Okay? You're always going to have 3 rows, and those rows are going to be the x, the f of x, and the f prime of x. Okay? And I'll tell you why I actually have this as 5 columns. Okay? The 5 columns represent these things. Start with your left endpoint. That's at x equals -1. You end at your right endpoint. That is x equals 3. And all of the guys that you found in between, all of the places where it's a horizontal tangent, put that in between. And you space things out. So you always go point, space, point, space, point, space, and so on. Okay? Now, those are the x values. The f of x is the y values, and I put it in black because that's where you go back to. You plug into black, and I guess I accidentally wrote this problem in red, but you go back to here to get your y values. So if I plug in -1, if I plug in 2, if I plug in 3, that's what I'm looking for. Okay? So I got x squared minus 4x plus 5, and I want to plug in negative 1. I get 10. So this is y equals 10. If I plug in 2, I get y equals 2. And if I plug in 3, oops, I think I messed up. Hold up. Sorry, when I plug in 2, I get y equals 1. That's my fault. And then when I plug in 3, I get y equals 2. Okay, those are plugging into the original. Okay, now let's plug into the derivative. So here's my derivative. I'm going to use that to plug in here. Now, 3 of them you already know. This guy's derivative was 0 because that's what we found. This was my horizontal tangent. Remember that one test or quiz you had? I called that a hot horizontal tangent. Okay, here, just on that last slide, I said you can't have derivatives at endpoints because it's like a teeter-totter. So this is undefined. Over here is undefined. And then the rest of this, I want us to do a sign check. So my goal here is I want on these two parts, the in-between parts, the reason I space it out this way is these parts I want a sign check. Okay? So we're going to sign test here. So I want the slope between x equals negative 1 and x equals 2. Any point you plug in between negative 1 and 2 is going to have the exact same slope, sign, positive or negative. So for me, the best number I would plug in is try x equals 0, because it's in between. If I plug 0 into the blue guy again, 2 times 0 is 0, minus 4 is negative. Here I might, in my head, try like a 2.5. 2.5 times 2 is 5, minus 4 is positive. Okay? With that, it is nice, because then now I can graph it. And I can go with a little bit more detail than what we quickly drew before. So I have at negative 1, it's at 10. At 2, it's at 1. So this is 2, comma 1. This is negative 1, comma 10. And at 3, it's 2. 3, comma 2. And it looks like this. All I know is right here is flat. So when I draw it out, I bet, especially since we know parabolas, it looks like that. Okay. Now, when you label these points, okay, this point here is the local and global minimum. Local means it's just kind of like Colorado. What is the local max in Colorado? What's the highest point in Colorado? Mount Elbert. Now, is that the global max? Is that the highest point in the world? No. What's the highest point in the world? Mount Everest. Now, is Mount Everest the highest mountain in the Nepal region? Yes. So you could say Mount Everest is the local max for the Nepal region, and it's the global max. That would be this point here, the local and global max. It's the highest point for that area and the highest point for this whole picture. Now this guy right here, he's a maximum. He's at the highest point in its little region, but it's not the highest point for the whole graph. So he's just called the local max. Okay? Now this one was very simple because it was a parabola. We'll do a couple more that are a little bit more intense. But I do want you to see that we're good with parabolas. Technically, it could have looked maybe like this. And this is the part that we need to work on, is where we have the same points, okay, that we drew. Here, here, here. And we know parabolas look like that. But what is it to say that I could have bent it a little bit different on the way down and made it a little bit more like an Elitch's or Waterworld slide? And on that part, you would notice that this here is concave down. And then this part here, all the way to there, is concave up. And then I try to make this version right here, that part I try to make is no concavity. Okay, that would have been where f double prime equaled 0. Here it would have been f double prime equaled a negative, and here f double prime equaled a positive. I don't know the concavity of the parabola outside of we've done parabolas for the last 2 or 3 years. So in this case, yes, we got lucky that we know parabolas, so we know that it bends the way that we predicted on these two here. But once we get to a little bit more complicated guys, I need to learn how to do the bend of the graph. And we'll really look at that next week. So I'm just kind of showing you a preview here of, yes, we know how to go down, flat, and up with the first derivative, but we need to make sure we know how to bend things as well. Another little preview is the word inflection point. Right when you turn from concave down to concave up at that red dot, think about turning a wheel of a car. Right when you turn your wheel, that's called an inflection point, and it's again where the second derivative is 0, kind of like where a line has a second derivative is 0 everywhere. Preview, but just realize I don't just care about how it goes up, down, and flat. I need to know how it bends while doing that.